Hello everyone, welcome back to the power quality lecture series. So in this video we are going to discuss about various power quality measurement equipment. So it is clear that power quality phenomena that covers a wide range of frequencies. So they include everything from very fast transient over voltages which is in the range of microsecond time frame to a long duration outages in the range of hours or days time frame. So the power quality problems also include the steady state phenomena such as harmonic distortion and the intermittent phenomena such as voltage flicker. And this wide variety of conditions that makes that make up power quality makes the development of standard measurement procedures and equipment are very difficult. Although the instrument have been developed that measure a wide variety of disturbances, a number of different instruments may be used depending upon the phenomena being investigated. And the basic categories of the instrument that may be applicable include wiring and grounding test devices, multimeters, oscilloscopes, disturbance analysis, harmonic analysis and spectrum analysis, combination and disturbance and harmonic analysis, flicker meters, and energy monitors. And this video we will discuss the application and limitations of these different instruments. Besides these instruments which measure steady state signals or disturbances on the power system directly, there are other instruments that can be used to help solve the power quality problems by measuring the ambient conditions also. And first we move on to wiring and grounding testers. Many power quality problems reported by the end users are caused by the problems with wiring and grounding within the facility. These problems can be identified by visual inspection of wiring connections and the panel boxes, and also with special test devices for detecting the wiring and grounding problems. So, and important capabilities of a wiring and grounding test devices are detection of isolated ground shorts and neutral ground bonds, and ground impedance and neutral impedance measurement or indication, detection of open grounds, open neutral or open hot wires, detection of hot or neutral reversals or neutral or ground reversals. So these three-phase wiring testers should also test for phase rotation and phase-to-phase voltages. These test devices can be quite simple and provide an excellent initial test for circuit integrity. Many problems can be detected without requirement of the detailed monitoring using expensive instrumentation. Then second one is the multimeters. So after initial test of wiring integrity, it may also be necessary to make quick checks of voltage and or current levels within a facility. So overloading of circuits, under voltages and over voltage problems and unbalances between circuit can be detected in this manner. These measurements just require a simple multimeter and various signals that can be used to check by using these devices are phase to ground voltages, phase to neutral voltages, neutral to ground voltage, phase to phase voltages in a three-phase system, phase current, neutral current, etc. And the most important factor to consider when selecting and using a multimeter is the method of calculation used in the meter. All the commonly used meters are calibrated to give an RMS indication of a measured signal. However, a number of different methods are used to calculate the RMS value. The three most common methods are, first one is a peak method. Assuming the signal to be sinusoid, the meter reads peak of the signal and divides the results by square root of 2, that is 1.414, to obtain the RMS. Then averaging method, the meter determines the average value of a rectified signal. For clean sinusoidal signal, the average value is related to the RMS value by a constant. Then true RMS meters, the RMS value of the signal is a measure of heating that will result if the voltage is impressed across a resistive load. And one method of detecting true RMS value is to actually use a thermal detector to measure the heating value. And in modern digital meters uses a digital calculation of the RMS value by squaring the signal on the sample by sample basis, averaging over the period, and then taking the square root of the result. So these different methods all give the same results for a clean sinusoidal signal, but can give significantly different answers for distorted signal. That is the point. So this is very important because significant distortion levels are quite common, especially for the phase and neutral current within a facility. Next type of meters. Before that, you can see that comparison methods of measuring voltage and current with multimeters. You can see the true RMS method and peak method and averaging method. And for a different type of waveform, like purely sinusoidal, square wave, triangular, and other distorted waveforms, how this calculation will be, how much it accurate. Then digital cameras, and the photographs are extremely useful for documentation purpose. So those conducting the measurements often get distracted trying to get the instruments to function properly, and the tests are coordinated. So the modern digital camera has become an indispensable tool when taking field measurements. So it is a simple matter to take a photographs to document the test. The photographer can immediately tell if the shot failed and retake it with a different field exposure. These are the typical items to record photographically during field measurements are nameplates of transformers or motors, instrumentation setups, transducers and probe connections, key waveform displays from the instruments, substations, switchgear arrangement, arrestor positions, etc. Then dimensions of key electrical components such as cable length, etc. So video cameras are similarly useful when there is a moving action or random events. Next device is oscilloscopes. So an oscilloscope is valuable when performing real-time test. Looking at the voltage and current waveform can provide much information about what is happening, even without performing detailed harmonic analysis on the waveform. So one can get magnitudes of voltage and current, look for obvious distortion, and detect any major variation in the signals. A digital oscilloscope with the data storage is valuable because the waveform can saved and analyzed. So oscilloscope in this category often always also have waveform analysis capability like energy calculation, spectral analysis, etc. In addition, the digital oscilloscope can usually be obtained with the communications so that waveform data can be uploaded to a personal computer for additional analysis with a software package. The latest development in the oscilloscope are handheld instruments with the capability to display the waveform as well as performing some signal processing. So these are quite useful for power quality investigations because they are very portable and can be operated like a voltometer (VOM), but yield much more information. These are ideal for initial plant surveys. You can see one of the such active harmonic analyzers. This particular instrument has the capability to analyze the harmonics and permits connections with the personal computers for further data analysis and inclusion into reports. The companies like Fluke is providing a harmonic analyzer. It is most widely used. Then disturbance analysis. So disturbance analysis are the disturbance monitors which monitor the disturbances from a disturbance monitors from a category of instruments that have been developed specifically for power quality measurements. Typically, they can measure a wide variety of system disturbances from very short duration transient voltages to the long duration outages or under voltages. Threshold can be set and the instrument left unattended to record the disturbances over a period of time if you are setting threshold. And the information is most commonly recorded on a paper tab, but many devices have attachments so that it can be recorded on a disk as well. And these are of two types of disturbance analysis. There is conventional analysis that summarize the event with specific information such as over voltages and under voltage magnitude, sags and surge magnitude and duration, transient magnitude and duration, etc. Then second one is the graphic based analysis that save and print the actual waveform along with the descriptive information which would be generated by the one of the conventional analysis. And it is imperative to have a waveform capture capability of a graphic based disturbance analyzer for a detailed analysis of a power quality problem. However, a simple conventional disturbance monitor can be valuable for initial check at the problem location. You can see one of the graphical based analyzer output shown here. Then next one is the spectrum analysis and harmonic analysis. So instruments in the disturbance analyzer category have very limited harmonic analysis capabilities. Some of the more powerful analyzers have add-on modules that can be used for computing fast, like a Fourier transform or fast Fourier transform FFT calculation, such type of calculations to determine the lower order harmonics can be used here. However, any significant harmonic measurement requirements will demand an instrument that is designed for a special analysis or harmonic analysis. Important capabilities for useful harmonic measurements actually include these things, that is a capability to measure both voltage and current simultaneously so that harmonic power flow information can be obtained, capability to measure both magnitude and phase angle of individual harmonic components, then synchronization and sampling rate fast enough to obtain the accurate measurement of harmonic components up to at least the 37th harmonic, and capability to characterize the statistical nature of harmonic distortion levels. And these are basically three categories of instrument to consider as a harmonic analyzer. First one is a simple meter. It is sometimes be necessary to make a quick check of harmonic levels at a problem location. So a simple portable meter for this purpose is this purpose we are using a simple portable meter. There are now several handheld instruments of this type on the market. Each instruments have advantages and disadvantages in its operation and design. And these devices generally use microprocessor-based circuitry to perform the necessary calculations to determine the individual harmonics up to 50th harmonic, as well as the RMS, the THD, and the telephonic influence factor, TIF. And some of these devices can calculate harmonic power also and can upload stored waveform and calculated data to a personal computer. Then second one is general purpose spectrum analysis. Instruments in this category are designed to perform spectrum analysis on the waveform for a wide variety of applications. So they are general signal analysis instruments. The advantages of these instruments is that they have very powerful capabilities for a reasonable price, since they are designed for a broader market than just power system applications. And the disadvantages is that they are not designed specifically for sampling power frequency waveform, and therefore it must be used carefully to assure the accurate harmonic analysis. So these are a wide variety of instruments in this category. And the third one is special purpose power system harmonic analysis. Besides the general purpose spectrum analysis just described, there are also a number of instruments and devices that have been designed specifically for power system harmonic analysis. These are based upon the FFT, fast Fourier transform with the sampling rates specifically designed for determine the harmonic components in a power signals. Then next type is the combination disturbance and harmonic analysis. The most recent instrument combine harmonic sampling and energy monitoring function with the complete disturbance monitoring functions is known as comes under this one. The output is graphically based, and the data are remotely gathered over phone lines into a central database. Statistical analysis can then be performed on the data. The data are also available for input and manipulation into other programs such as spreadsheet and other graphical output processes. And these are the examples of such kind of devices here. And you can see that one figure in This instrument is designed for both utility and end user applications and being mounted in a suitable enclosure, as you can see in this figure, for installation outdoors on utility poles. It monitors the three-phase voltages and current simultaneously, which is very important for diagnosing the power quality problems. And this instrument actually captures the raw data and saves the data in an internal storage for remote downloading. And also offline analysis is performed with powerful softwares so that it can produce a variety of outputs, such as you can see those output also here. You can see the total harmonic distortion, waveforms, etc. The figures are shown here. And you can see that the top chart shows a typical result for a voltage sag. Both RMS variation of the first 0.8 second and actual waveform for the first 175 milliseconds are again shown here in the first figure. The middle chart shows a typical wave fault up capture from a capacitor switching operation. The bottom chart, or you can right side, you can see that that particular chart demonstrates the capability to report the harmonics of a distorted waveform. You can see the waveform, distorted waveform, and its corresponding total harmonic distortion.